So in last lecture or last few lectures, I can say, two memory management schemes we have discussed. One is contiguous memory allocation and second one was segmentation. Now let us see this third memory management scheme, and that is a paging. Okay. What happens in paging is, as we already aware that there is a logical memory and there is physical memory, right? So physical memory is what we can call as our RAM, and logical memory is the addresses generated by the CPU, maybe by compiler. Okay, the addresses that can be seen by the CPU. Those are all logical addresses. Now, like segmentation, one of the advantages of paging is the process can be stored in the physical memory and contiguous space is not required. So non-contiguous space can be utilized by this scheme. Okay, and because of that, it usually avoids the external fragmentation. Even it avoids the problem of different sizes of holes. Okay. The scheme of paging is very simple. Let us see how it works. Physical memory will be divided into fixed size blocks. So for example, if I have say 32 MB of RAM, 32 MB I am saying, and now if I want to create a fixed size block of say half MB. Okay, half MB I am saying. So 32 MB will be divided into 64 equal parts. Okay, so here important thing is all the blocks will be of the same size, equal size. Okay, so physical memory will be divided into fixed size blocks, and these blocks are called as frames. So that is one important thing here, the frame. Okay, and this is typically power of 2. So maybe like from half KB to 16 MB. Okay, so that is the typical size, but that will be decided by operating system and the purpose of that. Now, like physical memory is divided into fixed size, logical memory is also divided into blocks, and the size of block will be exactly same like size of frame. Now try to understand the difference between frame and page. Okay, so anyways, both are blocks of same size, fixed size. Okay, and size of page and size of frame, that must be matched. Only thing is the blocks of logical memory are called as pages and the blocks of physical memory are called as frames. Okay, and now operating system has to keep track of all the free frames. So for example, as I mentioned, 32 MB of RAM is there and half MB is the size of block. Then total 64 blocks will be there. Now how many blocks are free at that time? Okay, so that maybe initially everything is free, then operating system is loaded. Say for example, operating system took 2 MB. 2 MB means if half MB is the size, 4 blocks will be occupied by the operating system. For example, I am saying. Now rest of the frames are free. So kind of linked list will be used there to keep track of free frames. Whenever process demands for multiple frames, maybe single frame or multiple frame, it will be taken from free frame and that will be allocated to that process. Okay, so that is how it works. Now to run a program of size n pages, because the size of page is equal to size of frame, if my program needs n pages, that means operating system need to find n free frames and then load the program. Okay. Now see, if you can remember, with contiguous memory allocation, we just needed the relocation register and limit register, single pair. But with segmentation, why single pair is sufficient? Because we have a single contiguous block. So once I got the starting address and the length, my complete process will be within that address space only. But with segmentation, we slightly modified it because each and every segment can be loaded anywhere. Now we'll have some sort of a segment table, okay? And segment table, it includes the base address and the limit register. So base and limit will be available there. Now here, why separate table is required? Because the memory required by the process is available at different locations. Just a minute. Okay, so we were talking about the segment table. Now the memory required by the process is available at different places, like depending upon how many segments are there. Exactly same manner, now whatever the n pages required by my program, okay, so these n pages can be loaded anywhere in the physical memory at any frames. So now which page is loaded at which frame number, that information we need to keep track, and that will be available in something called as a page table. Like we have a segment table, here now we have a page table. So page table will be used to translate the logical address to physical address. Even if you have some sort of backing store, then backing store is also split into pages exactly the same manner. Okay, so this avoids the problem of external fragmentation because the size of page and size of frame is exactly same, but still it can have internal fragmentation. Why it is so is very simple. Say for example, if my page size is 2 KB, okay, 2 KB I am saying, page size is 2 KB, so definitely frame size is also 2 KB, and if size of my program is say for example 1 KB, approximately 1 KB is equal to 1000, if that is the calculation, and if the size is 1200 1200 bytes. Now what happens is, first 1000, sorry, I mentioned size is 2 KB, no? So suppose for example 2300 is the size of my process. Okay, so let me repeat it. Page size is 2 KB, so frame size is also 2 KB, and now size of my process is 2300 bytes. Okay, now if I take approximate 2 KB means 2000 bytes, what will happen is my process or my program needs 2 pages, that means 2 frames. So first frame will be full 2000 bytes, and next frame, as I mentioned, the size is 2300, just 300 bytes will be loaded into the second frame, and remaining is waste. So that is called as the internal fragmentation. You getting it, no? Right. Now with that, how address translation scheme works is very simple. This is again exactly same like segmentation, where address is divided into 2 parts, the segment number and the offset. Same thing, only segment number is not there. We'll call it as a page number. So page number, let us call it as a P, used as an index into page table, exactly same like segment number. S was used as an index into segment table. Same thing. And page offset D, yes, same thing. So for given logical address space 2 raised to m and page size is 2 raised to m. So see, the number of bits is simply divided there. For example, the page offset number of bits mentioned in the diagram is, let me highlight it. If you can see it here, it is n. So page size is definitely 2 raised to n. Meaning of that is very simple thing. If n bits are utilized for page offset, let us call it as a 8. If n is equal to 8, then 2 raised to a is equal to 256. Right? So that is the page size. And m minus n that is utilized for the page number. Okay. So if 2 raised to m is the logical address space, so total bits are m. You simply do one thing, or m minus n plus n, that gives me m. So total number of bits is m. So total logical address is 2 raised to m. Out of these, n bits are utilized for page offset. So page size will be 2 raised to n. And now, how many pages will be there? It is very simple thing. If m minus n, those many bits are utilized for page number 2 raised to m minus n. That will be number of pages. I think there is one question on chat. How to determine the best size for the frame? Now it depends on what kind of operating system is there. The purpose of operating system. Mostly larger the size of frame is there is more wastage in case of internal fragmentation. If I again repeat the same example, for example, page size is 2000 bytes, and if 2300 is the size of program, then 2 frames will be allocated, that is 4000 bytes will be allocated, out of which 2300 will be utilized. So what is wastage there is 1700. Remember, 1700. This is the wastage. Now, if I reduce the same thing, say for example, if I make it 500, half KB, you can imagine, right? How many frames will be required is 3. No, not 3, 5. So 2500 is actually allocated space, out of which utilized will be 2300 and wastage will be just 200 bytes. Wastage will be just 200 bytes. Now, does that mean lesser size is better? Definitely not. Reason is, as the size is lesser, the length of page table will increase. Number of entries in the page table will increase, and that will take more time for lookup. Anyways, that also we'll see maybe in next few slides, because so for example, I just mentioned like 32 MB is I think it becomes more, but still if it's a 32 MB is my total memory, and if half KB is the page or frame size, how many frames will be there? So it is very simple thing, 32 MB divided by half KB. Okay, those many frames will be there. Now if it is 2 KB, then definitely it will be lesser than that. So the storage requirement to store the page table will be reduced. Number one. Number two, lookup time will be lesser. So definitely operating system has to look for what is the average size of programs that are submitted there, and depending upon that operating system has to come up with some optimal value for the page size or frame size. So we cannot say like lesser is better or higher is better. No, it all depends on the average size of your programs that are executed on. Not necessarily just that, other factors are also there, like how much cache memory is available with you. Larger the cache memory, you can store the page table into the cache. If it is lesser, better go with higher size of frame. Now, what is use of cache memory? Anyways, that we'll see in next coming slides. Okay. So let us move further. The paging hardware, how address translation is done. Now, whatever the address generated by CPU, that is the logical address. As I already mentioned, it will be divided into page number and the offset. Now, page number will be used as a displacement here, as an offset here into the page table, so that now remember, page table just have the frame number. Page table just have a frame number. Now that frame number will be taken here. Imagine like this is the base or location register for that particular page. This offset will be added into that. This offset will be added into that, and then we'll get the physical address for that particular byte. Now, this is exactly same like your segmentation hardware. Only thing is, in case of segmentation, we not just need the base address, but we need limit register, because in case of a segmentation, segments are not of the same size. They are of varied size, right? So we need limit register there. So if we go back, let me go back in the hardware of segmentation. See here, we have limit register also and base register also, because segments are of different size. So we need to check this condition if it is in limit of that. Now this thing is not required in case of paging. Reason behind that is very simple. The size of page is exactly same like size of frame. So no need to check that, right? And because the pages and frames are of the same size, we simply add this D into the base register. D is offset, and we get the physical address. So this is the paging hardware. Now how it looks like is something like this. Now you need to understand here the size of this page and size of this frame is exactly same. Okay. Then suppose there is one process with 4 pages, and these 4 pages can be loaded anywhere. For example, this page 0 is loaded here at frame 1, page 1 is loaded at frame 4, page number 2 is loaded at frame 3, and page number last, which is 4th, because the number started with 0, it is loaded somewhere here at frame number 7. This information will be stored in the page table. Now meaning of this is page 0 is at frame 1, page 1 is at frame 4, page 2 is at frame 3, and page 3 is at frame 7. So this is the page table. Okay. Now, can you see this? Let me check if I can zoom it. No. Is it visible for you? Okay, fine. So now let me tell you what is this. Let me tell you what is this. Suppose there is one program in which 16 instructions are there. Not necessarily instructions. It is the size of that program. Maybe data is there, instruction is there. For simplicity, a small example is taken. Okay. Now, what happens with this is the first instruction is A, next one is B, then C. Rather, I can say content of that. Maybe it is instruction, maybe it is data. Okay, so A, B, C, D, E, F, G up to P. Total 16 bytes are there in the logical memory of your process. Right. Now, the 4-byte pages are used here for simplicity. Just 4 bytes. That means the size of frame is just 4 bytes. Similarly, the size of page is also 4 bytes. Okay. And total 32 bytes memory is there. A very, very small number, but for simplicity, we say it is 32 byte memory. Now, meaning of this is very, very simple. If it is 32 byte memory, how many bits are required to represent this address? How many bits are required? Yes. 32 into 8. No. Total memory size is 32 byte. In other words, I just have exactly 5. 5 is correct answer. 5 is correct answer. Okay. How many pages will be there? Or how many frames will be there? How many frames will be there? 4. No. 4 into 4, it will give me 16. No. I am asking how many frames will be there. That means my physical memory is divided into blocks. 32 is also wrong answer because total size is 32 bytes. 8 is exactly correct. So 8 frames will be there. Very, very simple thing. Okay. 8 frames will be there. Got it. Now, if the size of page is 4 byte, how many bits are required? I think there is something wrong. There is something wrong in the diagram actually, because the size of this M should be here. This is wrong thing. It should not be 4. It should be 5. Somebody already mentioned that. Nikhil mentioned that. 5. Okay. So meaning of this is, let me tell you, we'll have something like this. Total 5 bits. Out of this, 2 will be utilized for the offset and 3 will be utilized for the page number. So definitely 2 raised to 3 will be number of pages, that is 8, and 2 raised to 2 will be the page size, and 2 raised to 5 will be the total memory. So in diagram, just one wrong thing is there. They have written it as a M is equal to 4. It should be M is equal to 5, not 4. Okay. Now let us call this as a page 0, page 1, page 2, and page 3. So total 4 pages are there. And now we have, this is a 0th frame. 1, 2, 3, 4, 5, 6, and 7. So 0 to 7 means 8. So there are total 8 frames, and the requirement of my process is just 4 frames because 4 pages are there. Okay. Now where ABCD is stored is somewhere at this 5th, actually 6th, because number starts with 0. So this is at the 5th frame. So that entry is made here. Now first one, like that is EFGH. EFGH is just below there. So it is at 6th. So that entry is made in the page table. Now IJKL, yes, it is available at first frame number, that is second frame. So next MNOP, that is at second frame. So that is how table looks like. Okay. Now as I mentioned the addresses. Okay. Now if I want to talk in terms of binary number system, so for example, if I give address something like this 0, 1, 0, 1, 0. If this is the address, logical address rather, I can say 5-bit. Okay. Can anybody tell me this address refers to which alphabet? Because we have stored alphabets in the memory. This refers to which alphabet? First of all, in the logical memory. Then we'll try to locate it at the physical address. 01010. This refers to K, D. No, D is not there. I think K is correct answer. Now see how to locate it. First of all in logical memory and then in physical memory. As I mentioned, we have a 5-bit long address, out of which first 3 bits will be utilized for page number and next 2 bits will be utilized for offset. Okay, so that definitely gives me some sort of, for example, these first 3, what is value of this? 010 gives me 2. It gives me 2. Logically speaking, that is third page. That is okay because page number starts with 0. But this value is what? 2. And this 10 gives me what? The offset. And 10 is also 2. Now meaning of that is this second byte, this gives me second byte from second page. And because of our number starts with 0, actually it is third byte from third page. So this is page number 0, 1, 2 and 0, 1, 2. So this definitely gives me K. This definitely gives me K, right? Now how to identify address? How to identify address in physical memory? For that you need to consult this page table. Now remember what we did in case of segmentation is we have stored the starting address, that is the base address for each and every segment. But here in page table we just stored the frame number. Given the frame number and the size of frame, it is just a matter of multiplication, right? If my number starts with 0, and for example, if I need the starting address of, say for example, frame number 2, if the size of page is 4, it is just 2 into 4. That's it. Okay. Now the same thing, what I'll do is I'll have a lookup for page number 2, which is located here, which says that page 2 is stored in the frame 1, right? So from this I am getting frame number 1 multiply by size of page, that gives me 4, plus this we need to add, that is the offset. So 4 plus 2 gives me 6. Now you can check it here. So at address 4 I is there, at address 5 J is there, and at address 6 K is there. So whatever the alphabet we are looking into the logical memory, the same alphabet will be located in the physical memory. Okay. In case of segmentation, we are doing some sort of addition because we are directly getting base register there. But here, as we are getting the frame number, fine, frame number multiplied by page size, that gives me the starting address of that frame, plus whatever the offset is there, that gives me the address of that byte from logical memory to physical memory. Any doubt in this? Is it clear? There is a question from Sagre. Is a cache memory? We'll see later on because it is coming there. It is coming there. Why we need cache memory? That is first part, and then how to utilize it. That is the second part. Cache memory will be coming soon. No problem. How you understood this paging example? A simple example. Fine. So let us move forward. How to calculate the internal fragmentation? Now that is very simple thing. For example, I just given the similar kind of example. The page size is, say for example, 2 KB. Size of process is something like 72,766 bytes. That roughly comes to, for example, if I divide it 72766 by the page size, what is the answer you are getting? 72,766 divided by 2048. That gives me something like 35.53. So definitely 35 pages are required first upon, plus something, and that plus something is nothing but we need one extra page. That means we need 36 pages. Okay, so 2048 multiplied by 36. So total memory allocated will be, it is around 73728, 73,728. Now if I subtract the size of process, that is 72766, you will come to know that 962 bytes is the internal fragment. Excuse me, just a minute. Okay, so 962 bytes will be the internal fragmentation. Now what will happen in worst case is very simple thing. One page is completely utilized and just single byte is required from next page. So that is the one frame minus one byte. So that is the worst case. Okay. Best case is what? Size of process is exactly multiple of page size. Exactly multiple. So there will be zero wastage. So that will be the best case. Worst case is what? Just single byte is utilized from that frame. So in this example, if the page size is 2048, the wastage is 2047. Okay. Now, as usual, if we do some sort of averaging, okay, so average fragmentation will be half of the frame size. Now that was the question asked by somebody. So does it mean small frame size is desirable? So answer to that is, again, as I mentioned, no, because each entry in the page table, it takes memory to track. So size of page table will definitely increase in that case. Okay. So what is the best approximation? Now that has to be decided by the operating system based on some historic data. For example, if you see the Solaris operating system, previously Sun Solaris, now it is called as Oracle Solaris. Now that supports two page sizes. One is 8 KB and one is 4 MB. Now see, one is 8 KB and one is 4 MB. Okay. So for example, if the process is too big, maybe they will adapt from 4 MB. They will allocate from 4 MB. Something like that. Okay. Now, I was talking about the free frames. Definitely some sort of linked list kind of thing is required in order to keep track whenever memory is required. No need to scan through all the frames in the physical memory to check whether it is free or not. Operating system does simple thing. Now if you see this diagram, before allocation, frame number 14, 13, 18, 20 and 15. So those are in gray shade. For example, here, first of all 14, then 13, 18, 20 and 15. These are free. And if this is the new process whose demand is 4 pages, then what will happen is from this free list, for a page 0, first free frame will be utilized. So page 0 will be loaded into frame 14. That is what this page table is. Next page will be loaded into the next, that is 13. Page number 2 will be loaded into frame number 18, and page number 3, that will be loaded into frame number 20. So 4 pages required, 4 frames. Now one will be free. So frame number 15 will be still free. Okay, so this process will be loaded into the memory, like page 0 is loaded, page 1 is loaded, page 2 is loaded, and page 3 is loaded. And this new processes page table is something like this. Okay, when such a process is finished, then these frames will be again added back into the free frame list. Got it? Now, how to implement these page tables. So very first thing is, like segment table is in the memory, we need to store the page table in main memory. Now for segment table, we have something called as a STBR, segment table based register. Exactly same manner for that particular process. If the page table is in main memory, it is always actually in the main memory. Okay, then where it is in the main memory, that information will be kept by one of the register called as page table based register. And again, the number of pages vary from process to process. We need to see how many entries are there in that page table. That will be indicated by page table length register. So that indicates the size of the page table. How many pages are there? Something like that. Now with this scheme, what happens is whenever you want to access data or instruction, you need to access memory twice. Correct? Why twice? First upon, to see the page table, and second time after calculating address to access the actual byte, maybe data or maybe instruction. So one memory access is required for page table and next one is required for data or instruction. And as we already aware, memory is comparatively slow. So that actually creates problem. Like for each and every instruction, I need to consult, I need to access the memory twice. And memory is slow as compared to processor. So that is like a performance bottleneck. Okay. And now there comes into picture the cache memory. Cache memory is very fast as compared to memory. I can say tentatively we can say it's like less than 90% times required. So access time of cache memory is say within 10% as compared to what I can say main memory. So if 100 nanoseconds are required to access the memory, then cache memory requires less than 10 nanoseconds, something like that. that is just to tell you the relative speed of cache memory and the main memory. Okay, that is one thing. And second important thing is they have a fast lookup. That means cache can be looked up as associative memory. Let me tell you what is associative memory again. Suppose you have array in memory. Array, I'm talking normal C++ array, and I'm talking about main memory. Say for example, you have an array in memory with 100 elements, and I'm looking for some number X. Okay. Now what is the time complexity for that? So worst case, I need 100 comparisons. Best case, maybe within one comparison. And then average, it is in terms of notation, it is big O of n, where n is the size of that. Right? That is the normal memory, where we look for first element, then second, then third, then fourth, fifth, sixth, seventh, eighth, so on, so forth, till say for example, as I mentioned, 100. So up to 100. Associative memory is not like that. It can look parallelly in all the locations. So with only one comparison, I'll get whether it is available there or not. Now how that is implemented? Yes, that is hardware part. But just right now remember, it is associative memory which has the capability of special fast lookup. It can look up into all the locations simultaneously. Okay. And in operating system, that is called as TLBs, translation look aside buffer. So that is used for translations, like page number will be translated into the frame number, something like that. So very first thing is why we need cache. We need cache memory because memory is slow, and for each instruction or data we need to access memory twice, so that reduces the performance. So these TLBs are used. Okay. Now how to use it? How to use it? Remember that the TLB entry, basically the cache is very small, very first thing. And because it is very small, if for example, if I have say 50 processes, I cannot store cache for all 50. No. So whenever we are switching from one process to other process, maybe we need to flush the cache. So whichever currently running process, I'll just have TLB for that process only. Okay. Now there are two operations or two things we can say. One is called as TLB hit and TLB miss. Okay. Now, what is that? What is that? Maybe we need to move to the next slide. Okay, this is, I already mentioned, associative memory is parallel search. So if P, that is the page number, is in associative register, automatically with single lookup will get the frame number. Okay, so that is what the parallel lookup is there. Yes, exactly. Now this is the paging hardware with the TLB. And see, that is the reason why multiple arrows are used here. If P is given, it will look parallelly into the TLB. Now TLB is what? Translation look aside buffer. So actually this is a cache memory. Now see how it happens is, whenever CPU want to refer to data or instruction, logical address will be used. Okay. Now this page number from logical address will be passed to the TLB also. If it is available there, then that is called as a TLB hit. If it is not there, it is called as a TLB miss. Now if it is, you may wonder then why we are saying if it is there or not. As I already mentioned, because the size of TLB is very small, if page table of process, if it don't fit in the TLB, actual complete page table will be available in the memory and some part of that will be available in the TLB. If that page number is available there, we call it as a TLB hit. In that case, no need to consult the page table in main memory. We'll directly get frame number from TLB itself. Okay. So remember this frame number, in case of TLB hit, we'll get it from TLB, that is buffer. If it is TLB miss, we'll get it from page table. So definitely this will be slower, whereas this will be faster, because access time required for TLB is very less, and then we'll convert it to the physical memory. So it is exactly same like your previous slide of paging hardware. Only thing is this time we have added one part to it, that is the TLB, and two operations, TLB hit and TLB miss. Where meaning of TLB hit is page number found in TLB, and TLB miss means page number not found in the TLB. Okay. Now when we introduce this cache, let us call it a TLB only. What is the effective access time? And for this effective access time, a small calculation is done here. We will just finish this slide and we'll stop here today. The associative lookup time, let us call it as epsilon. So this symbol is epsilon time units. As I already mentioned, this can be less than 10% of memory access time. So the time required is just 10%, up to 10% I can say. Okay, and let us call alpha as the hit ratio. Hit ratio is what? TLB hit ratio. This is the percent of time that a page number found in associative register, that is in the TLB. Okay. Now, suppose 100 nanoseconds are required for memory access and 20 nanoseconds are required for TLB search, and alpha, that is the TLB hit ratio, is 80%. Then effective access time is calculated something like this. Now this is actually a very simple thing. Why? Because alpha is the hit ratio if it found there the one, what is one? One memory read is definitely required, irrespective of whether TLB hit is there or TLB miss is there. Now, because we are talking about hit, TLB hit, why? Because I am multiplying it by 80%. Okay. Whereas in other half, if you can see, it is 1 minus alpha. That means it is TLB miss. So 1 minus alpha, see 80% is what? 0.8. So what is the miss ratio? It is 20%. So that is 1 minus 0.8, that gives me 0.2. But remember, for that, we need two read operations. One is for page table and one is for actual data or instruction. Anyways, plus epsilon is required because in case of miss also, we need it. And now if you solve it, it is something like 2 plus epsilon minus alpha. That is the effective access time. Okay. So for example, the same thing is given here. If alpha is 80%, epsilon is 20 nanosecond for TLB search and 100 nanosecond for memory access, then effective access time is the same, just values put into the above formula, and then what we get is 120 nanoseconds. Can you imagine the performance gain here? Because if there is no TLB and just memory access is there, which needs time of 100 nanosecond, once for page table and once for data or instruction. So it is 2 times memory access time. So 200 nanosecond. It is 200 nanosecond. That is reduced to 120 nanosecond. But if we see the more realistic hit ratio, let me tell you why this is more realistic also. Because what happens is whenever TLB miss happens, that means that page is not there in the cache memory. Then operating system fetches that page into cache memory. So that what will happen? Next time, if the same instruction coming from the same page, it results into TLB hit. Now imagine if half KB is the size, that means 512 data or instructions, 512 bytes. TLB miss will be something like just for first access. But for remaining 511 times, you will definitely get TLB hit. And that is the reason for more realistic hit ratio is 99%. And if the same times is required for search, that is epsilon is equal to 20 nanoseconds and 100 nanoseconds for memory access, it results into 101 nanoseconds only. So just one extra nanosecond. That is the power of cache memory. That is the power of cache memory. Are you getting it? Any doubt? Any doubt? So today we'll stop here. Let me stop recording.